Well, now we want to find out what the rational roots are given a polynomial function using that rational zero theorem that we practiced just a minute ago. So here I have the function x cubed minus 2x squared minus 11x plus 12. And I have a list of steps that I'm going to go through in order to find what the rational roots are. First, let's talk about what the degree of the function is. The degree of my function, since it's already written again in its descending order, is third degree. What that tells me is since this is a third degree polynomial, I will have at most 3 real roots. At most. That means I don't have to have all 3, but I won't have any more than 3 real roots. Okay. Now we want to list the potential zeros of my function, and that's what we practiced in the previous video. So to do that, to list all of the zeros, what are we going to do? We first need to identify all the factors for p and all the factors for q. So for p, I have plus or minus 1, 2, 3, 4, 6, and 12. All of these factors are, or all of these numbers are the factors of 12. Q is just a 1, plus or minus 1. So P over Q is going to be just all of the plus or minus, this whole list for P's. Plus or minus 1, 2, 3, 4, 6, and 12. Now, what do I do with that list of potential zeros? The rational root theorem says that if this is the list of the potential zeros, then I have a zero lurking somewhere among this list. Now, a long time ago, we would take each of these numbers, both the plus and the minus, plug them in for x, and whenever we evaluated the function at one of these numbers and it came up to be 0, so if I replaced x with one of these numbers and I evaluated it to 0, then that one number was a 0 for the function. So I would have to do that. How many is that? 1, 2, 3, 4, 5, 6 times 2, 12 times. Okay, I don't want to do that, so I'm not going to. What we're going to do instead is we're going to let the calculator evaluate the function values for me. So I'm going to go and I'm going to put this polynomial into the y equal portion of my calculator, which I have already done. Let me pull both of these up. Okay, so you can see here that this right here is my polynomial function. It's on the y1 portion of my calculator, and I'm going to go let the table evaluate the function for me. If you don't have this already set up in your calculator, you want to make sure that you go to second window, have your table, your independent variable set to ask. Okay, so in other words, independent was my x value, dependent is y. So I'm going to put in an x value and the calculator is going to give me back the y value. So I'm going to now go to my table. So I do second graph, and you can see nothing is filled in for my x or my y's. I'm going to switch back over to my list. Remember, I have all 12 values here that I can plug into the calculator, and I'm looking for the first one, whichever one it is. I'm looking for a value that's going to return a 0 for me. So let's just pick plus 1. So if I enter 1 into the calculator, I get back 0. Okay, that's generally how it goes. It's the very first one that I picked. So that tells me that when x is equal to 1, that there is a 0 there for the function. So rather than having to go through that entire list, all I did was find out that when x is equal to 1, we have a 0. Now how do I write that in its factored form? It would look like x minus 1, right? If this is the 0, this is it. This is how we write it in its factored form. So that was the testing the list. We can check the graph if we want. I'm going to go back and show you what it does look like. So here I have it graphed, and you can see that right here is where we are crossing the x-axis at 1. So I know it's a it's a 0. Now we're going to come down and we're going to use synthetic division to partially factor this polynomial. Because if x equals 1 or x minus 1 is a factor of this, then I can divide this polynomial by this factor to reduce it so I can maybe factor it using the quadratic formula or something. So we're going to use synthetic division with this factor here. So I'm going to start with 1, put my upside down house there, and let me scroll up. I'm going to use synthetic division on the polynomial up here. So I have a 1, negative 2, negative 11, and positive 12 that I'm going to do synthetic division on. So we set this up by bringing the 1 down. Now we multiply and add. So that would be a negative 1. Multiply would be 1. Add straight down would be negative 10. Somewhere along there, I didn't do that right, so I missed a negative apparently. That's because that's a negative. So this would be negative 12. And 1 times that would be negative 12, add to be 0. Now how did I know I did something wrong? I could tell that I wasn't going to get a 0 down here for a remainder. Remember that if this is an actual factor of my polynomial that I started with, then when I do synthetic division, this should have been a 0. So that's how come I knew I was doing something wrong. Okay, so we have it factored, or we have the synthetic division done. Now what does that leave me? If I were to rewrite these coefficients into the remaining polynomial, right, what I just factored this into, this looks like x squared minus x minus 12. That is a quadratic equation that I know that I can factor. So that was your next question. Can I factor what I just did synthetic division on? Sure I can. So let's go back and we're going to rewrite what we've got so far. F of x is equal to my first factor I found, x minus 1, times this quadratic, x squared minus x minus 12. And I'm going to take that and I'm going to factor this guy. So I have x minus 1, and I just use trial and error on this. I know that this trinomial breaks up into an x and an x. This second sign tells me I have to have both a positive and negative. So what are the factors of 12 that subtract to give me 1? And that will be a minus 4 plus 3. So look, I now have my polynomial, my third degree polynomial, broken up into its factors that you see right here. So depending on the question, I can either stop there because I rewrote this function as a form of its factors, or I can go one step further. Oops, I got a lot of windows opening here. Or I can go one step further and I can solve, which is down here. I can solve the roots if I want also. Remember, that's when I take this and set the polynomial equal to 0 and use the zero product rule to solve each of these roots. X minus 1 equals 0, x plus 3 equals 0, x minus 4 equals 0. So I have zeros occurring at 1, negative 3, and positive 4. If you look back at our graph we had, I have 1 here, I have 2, 3, I have a 4 here, and I have a negative 3 here. So that is how you will take a polynomial, put it in its factored form to solve for its